Welcome to Session 2 of Impedance Analysis of Piezoelectric and Ultrasonic Transducers. We'll first go over the outline of this session. We're going to go and cover the basics of the resonance phenomenon. I think without a deep understanding of this topic, analyzing resonance behavior, phase, amplitude changes for the piezoelectric frequency response will be not clear. So we'll go over and get this basic theory explained and completed. So we'll talk about the two types of resonance or resonator behavior that we find in the first, and both obviously in piezoelectric devices. So the first we're going to talk about mechanical resonance, and that happens in a mass spring damper system, kind of boiling that down to the very basic level. The next is the electrical response. So just like the mechanical system has oscillation, has resonance, we also have the electrical response with the inductor, capacitor, and resistor forming a similar construct, actually mathematically very much equivalent to the mechanical response. Then we'll get into the meaty part of the subject, which is talking about the piezoelectric resonance, which is actually a electromechanical phenomenon. So the piezo resonance, we'll talk about piezoelectric forcing. So just like you have voltage or force in a mechanical system, or you have in the electrical system, you have voltage applied. You also have, obviously, if you have a piezo actuator, you have voltage applied and how that becomes force. We'll talk about that. And we'll talk about piezo resonance from a mechanical perspective, which is a bit easier to understand than the piezo resonance from the electrical perspective. But nonetheless, it's going to be both of them combine and are consistent with each other. And finally, we're going to be speaking about distributed system resonance. During the whole discussion until this point, I'll be mainly focusing on 1D analysis, where we have discrete components. But after this point here, I will start to describe more about distributive system resonance and its implications for piezoelectric devices. Obviously, when you build a device, for example, if you have a piezo material, let's say that's your piezo material, and you have a mass sitting on top. Let's say you have a mass like that. And this is a piezo, let's say. You may think that, well, let's just simulate this as a spring, and we'll just have that as a mass. And this is our system. However, the piezo itself has mass, and the mass actually has stiffness, and it's not a point mass, so it also has other, in this case it has edges sticking out. So actually when it resonates, it's going to start, these edges will start to, you might even say flap around, and that has to do with the speed of sound, and it gets to be a little bit more complicated when you start talking about distributed systems where there is mass and stiffness present, and also many types of vibrations, bending vibrations, which is called transverse displacement, and also longitudinal sound. So now we'll talk about what is resonance. If you think about a system with oscillating behavior, and one of the most simple systems that you are introduced to as a child is a swing. So you have some type of pivot point, and then you have your swing here, and you have a child sitting on it. And there are many, and they go back and forth. So there are two types of energy that are that energy is oscillating in between or going in between two types of energy, and that's obviously potential energy. So as the child goes up and down the swing, they're also getting farther away from the ground, and that is potential energy in terms of gravity. So mass times gravity and the height, and that gives you the potential energy. There's also the kinetic energy. It's 1/2 mass velocity squared. Also, you could do the angular version as well. But basically, you have energy going in between two systems. One is potential energy and kinetic energy, but you could call them whatever you like in terms of storage. Potential energy in terms of a mass spring damper system, as we'll be describing, is displacement of the spring, in which holds force and energy, the ability to do work once that spring is released. So in these type of systems, every time you push the swing, a certain amount of energy is lost. So a certain amount of energy is lost per cycle. This is also another important thing to understand. So when you push, there will be the child will stop, but not all the energy is lost per cycle. So there is a transfer of energy between the potential and kinetic, or the two storage energy mechanisms, which are trading energy, and the maximum potential energy is also equal to the maximum kinetic energy. And this energy is lost over time if you don't put more energy in, but not all of it is lost per each cycle. Therefore, with one push, you'll have a couple of swings back and forth, but in order to keep it going, you have to keep pushing. The other important point here is that energy accumulates. So as you're pushing, the amplitude will get larger and larger. Like if you're pushing your child, you'll get larger and you'll get larger amplitude, and eventually you'll saturate, like you can't push the child any farther. So energy accumulates, and this also has to do with the frequency of application of that force, of the way you're introducing additional energy into the system. You could actually move the pivot point of the swing back and forth to introduce energy. That would be scary, maybe a little bit dangerous, but you could do that. Or you could also push the child. That would obviously require some type of mechanism, machinery probably to do that. Depends on frequency. So let's take the example, and kind of the hypothetical example, that you were able to hold on to the swing at all points. Okay, you were stationary, you were able to hold on and apply force wherever, like you could apply your pushing force, whether the child was at the bottom, the lowest point of the swing, the highest, or the farthest back, which usually is not the case. You have to wait until the child is at your own height until you're able to push them. So, but let's say you could push all the time. This is our assumption. You can push all of the time because we want to get away from those physical constraints and get into something more mathematical and perhaps more applicable in general. So let's say you can push all the time. So the first case, let's talk about a couple specific cases. The first case is you do a very slow push. And let's say the amplitude of all of these pushes are the same. So every time you give a push, you are giving the same amount of the maximum force you're giving is the same. But let's say you're doing a very slow push. What do you think that would happen? Now, kind of logically, you would have a small amplitude. You wouldn't go very high up the swing. And your force, the applied force would also be in phase with the displacement. So however you apply that force, the object or the child or in whatever resonance system, that force would be going at the same pace as the displacement or the movement. So there would be completely in sync. And the opposite case is if there's very fast push. This is almost be looking at almost like shaking. So if you're shaking, what actually happens is your force is actually completely out of phase with your displacement. In fact, as you're pushing away, the displacement or the movement is toward you. So you're almost like shaking. So it's not very productive at that point. There's going to be a small amount of movement, but there's not going to be anything large, and it's going to be highly ineffective and a little bit, let's say, dangerous, and probably a child would fall out at that point. And also, what happens if you do it just right? So these are talking about frequency. This is a low frequency. I'll just write that low. This is a high frequency, so it's very high. Maybe there's a frequency in the middle of these two somewhere, and there is. So let's say you do it just right at the you do that push just right. At that point, if you have your force in phase with your velocity, which is also just by chance out of phase, 90 degrees out of phase with your displacement, and this is obviously fundamental relationship because of the different differentiation of a sine, and then you get a cosine, you get 90 degrees. So if you do it just right, what will happen is as you're pushing your child, you'll get higher and higher amplitude, and eventually you'll saturate. So this just right part is actually a natural part of the system of pushing your child, because you can only push them as they return, and that is the exact right point then to push them again. So you are in effect pushing them close to the optimum point. I think the optimum point would be when we have the fastest velocity at the bottom of the swing, and that's not possible. You have to push them when they get back to you. So which will be slightly out of phase with the perfect timing. For practical reasons, you can't do that. But there is a sort of timing that when the child returns to you, then you push them. It's sort of ingrained in the swing. But in other resonant systems, it's not that obvious. So pushing them just right provides the maximum amplitude. However, this causes the energy to start to accumulate in the system. So as a recap, what is resonance? Well, we have a system where there's two energy storage mechanisms. So so we can have oscillation. And at a very high frequency, at a very low frequency, there is small amplitude. I'll just do that. And at a very high frequency, there's also small amplitude. But at the resonant frequency, which is the the Goldilocks or the just right frequency, the energy stored keeps increasing because you keep delivering energy, and the energy keeps getting stored and increasing in the system. Therefore, if the energy stored increases, your velocity and your amplitude are, and your, let's say, the height are going to continuously increase. And obviously in a real system, you'll start to get nonlinear, and the swing will flip over the rail or the bar. That's a case we're not considering. And this continues to increase and increase and increase until this situation happens, that the power or the rate of energy that you're putting into your system equals the power dissipated. So you're able to, so a person pushing at a certain force is going to, at a certain point, the losses in the system, you could say, are going to equal out to the energy input. Because as you're increasing in speed, you're also increasing in losses per cycle. And assuming that you're putting force in or energy in at a certain power, maybe that trend is not non-linear, because when the person is going faster, you're able to put more energy for the same force. But eventually, that's going to equal the dissipated energy, because as something goes faster, if you just, we'll go over this in a second here, but we know the damping of a mass spring damper, the damper is related to velocity. And in a resistor, the damping ability is related to the current. So as these values increase, the power I squared R, that's going to dramatically start to increase until these two are equal. The rate that you're putting in power and the rate it's being dissipated. And that's when you peak out. So kind of, when you're decreasing your dissipated energy, let's say you're using really good lubrication, you will be able to achieve a significantly higher level of oscillation. The other very important point that will come up over and over again now is there's going to be a change in phase between the forcing function, whether that's going to be voltage or forcing, and output. And then again, that output could be current, it could be charge, it could be velocity, it could be displacement. But the forcing and the output will have a change in phase between and at that resonant point, which is a transition point, as we'll discuss in detail. So let's go over the mechanical resonance. So we have a mass, and these are ideal components without any geometry. So we have a point mass, and we have a forcing function. So we are applying a force, we're applying a force, and that force is a function of time, and it has a frequency associated with it. We have a spring, and we have a dashpot damper. And you probably are very familiar with this equation that describes the the system, the mass, and we have, let's say, we also have a position as a function of time. So the mass times the acceleration subtracted from the damping coefficient, or multiplied by the velocity, and we have the spring constant multiplied by the displacement, because the energy stored is exactly equal to the spring constant, a function of the spring constant and the displacement. And that's going to equal your forcing function with time, and probably, as if we generally describe a forcing function, it's going to have an amplitude, and it's going to be in phase with itself. So we won't write any phase out here. In general, it might have a phase, but if you reference your outputs from the input, which is the force, then you don't have to describe that with any phase value. From here, the method of analysis would be to describe a function which relates your inputs to your outputs. So now we're going to go and head toward the path of understanding, well, if I put in a certain force, then what displacement am I going to get, and amplitude, and what phase will that be between it and the forcing function. So usually that we describe that as a transfer function g, and the forcing function, or the transfer function in general, has an amplitude and a phase. So if we draw these sort of absolute value that describes the amplitude, and we also have a phase value associated with it in general. So because we have amplitude and phase of a resulting waveform, and we have an amplitude of the input. This will relate to the output, which we'll write as XO, because we could also describe our position and as I mentioned earlier, we're going to have a phase angle associated with that. And they'll have a position, and these are already amplitudes. It'll have a force, and this will have a phase. Or we could have written it like this. That amplitude. This is going to be simpler for us. So we're going to have a phase, and we're going to have a relationship between the amplitudes here. Now we will plot this. This is a function of frequency, and this is just the comparisons of the amplitude. How far or how high is this mass going to get as a result of a force at a certain frequency with an arbitrary amplitude input? Because according to a linear system, which these equations are describing, if you increase your force at any frequency, your output will increase by that same ratio or factor. However, the relationship, and that relationship only holds up at a specific frequency for such a linear system like a mass spring damper. So we have our transfer function, and we'll write that with absolute value bars. So again, if you multiply a force, so a force times the transfer function is going to give you your amplitude. So the higher this transfer function is, the larger the amplitude is going to be, according to your input force. So we'll draw our transition frequency, and we'll just draw a point there. We'll draw our low frequency point here and our high frequency point there. So what happens here at low frequency, we have approximately a steady amplitude when the frequency is much smaller than our resonant frequency. At the resonant frequency itself, we have a maximum amplitude, and as you keep increasing in your frequency, because as the frequency increases, the velocity and actually the acceleration increases by square root of that number of the displacement, because you take the derivative twice of this number, you end up with frequency squared. So in general, this relationship exists where you have your displacement amplitude multiplied by the frequency squared equals your acceleration. So the acceleration keeps getting higher and higher, which actually provides an opposing force for that mass to move. So you actually have lower and lower displacement as you increase frequency. But as you're going at a very low frequency, you're dominated by your stiffness. So here, the stiffness of your device is going to, or your system is going to determine the amplitude. On this side, your mass is going to determine your amplitude, and here you'll have the whole system dynamics determining the amplitude, especially the dashpot or the damping mechanism. Because as we described earlier, as I described in the previous slide, if you have low damping, if you have a very smooth, a lot of lubrication, then you're for a certain input power, you'll be able to achieve a lot more stored energy. It'll take a lot more amplitude for that dissipation to occur. So the result of that will be a higher peak. And you'll also have the peak will be more sharp. It'll also be of a larger amplitude. So this describes the input and output forces. So input force, output displacement. Low frequency, it's governed by the stiffness of the system. If you have a very low stiffness system, you will also have a very high amplitude. And as you go in very high in frequency, you're practically shaking the system at that point, and it's actually going to displace less and less as you keep increasing your frequency. At the resonant point, you're kind of governed by all of these factors. The resonant frequency itself can be solved for, and that's going to equal your stiffness divided by your mass, the square root of that number. This is the angular frequency of resonance, and this equation holds the angular frequency and the resonant frequency. This is radians per cycle. This is radians per second, and this is cycles per second on that side. So as you increase your stiffness, your resonant frequency will also increase, and decreasing your mass or increasing your mass will also cause a shift in resonant frequency accordingly. So we've described now the amplitude relationships between if you have a given input force and I give you this curve, let's say as a function, you have the specific points, then you'd be able to calculate your output. And also, given these distinct components, the mass, the damping of the system, and also the stiffness, you'd be able to calculate specific values, and you'd be able to determine this curve, and that has to do with the solution of this equation. So let's complete this. Now we had two components. We had our amplitude, and we also had our phase. And as we know, this number, again, it's equal to the amplitude divided by the amplitude of the output divided by the amplitude of the force. So we also had phase. So go ahead and describe that relationship. So I mentioned, and we talked about, and we'll draw a couple of points here. We'll draw, this is 0 degrees. This is 90 degrees. Here is negative 90. That'll be serving. And I'll just put this point right there as negative 180. So as we are starting, I mentioned at a very low frequency, your forces are exactly in sync with your displacement. So you're basically at this zero degree point right there. You're not moving, assuming we're drawing right now, we're drawing the phase in between the voltage, in between the output displacement and force. So we're in phase. So as we start to increase in our frequency, and we go toward the resonant frequency, which I'm going to draw it parallel to the top to the top plot. We go through a point where at the resonant frequency we are at negative 90 degrees, and I'll explain the significance of this, why it's negative 90 in a second. Then as we continue to increase in frequency, we end up by negative 180. So what this practically means, if you look at the time and amplitude plot, if you have force as a sinusoidal curve, at this lower frequency portion, you'll have your displacement at the same phase. But as you increase in frequency, and let's say you get toward your resonance point, you'll be at negative 90, which actually in this case means that the forcing function is lagging the output. So the forcing function is lagging the output. As you know, when you have a negative phase, then it makes it goes into a positive direction. So this negative 90 degrees phase lag here indicates the input is lagging the output by negative 90 degrees. And as you continue to increase the frequency and you get toward your final point, and as you continue to increase in frequency and you get toward your final point here, well, you have your displacement opposing your input force. There'll still be, it won't be exactly negative 180 degrees, or otherwise there'd be no transfer of energy occurring. However, and it begins to approach negative 180 degrees at those higher frequencies. In order to better understand force transfer and energy transfer because the power input into the system, it's better to look at velocity. So velocity is out of phase, is ahead. So if we had at lower frequency, we had displacement here. Velocity would then be lagging displacement by negative 90 degrees. This is a cosine, this is a cosine, this is a sine. So this is velocity, and this is displacement. So you actually start up here. And at its resonant point, or which is the same as the other displacement, because these are fundamentally related, there's no variation in their relationship. We have this performance. So at lower frequencies, we have 90 degrees, which is kind of standard. At the resonant frequency, we're in phase with voltage. So the phase equals 0 degrees. And after the resonant frequency, the phase continues to decrease until you get to negative 90 degrees. And the way we can best understand this is the power input, specified by a certain time, force times velocity. So we have this equation kind of relating the input power, or if you did the integral, obviously you'd have joules, or joules of energy input over a certain velocity. So this, in effect, basically tells you that as long as the force is moving, as long as the mass is moving in the same direction as the force, you obviously have the common equation, force times ds, or basically force times the distance traveled. That's going to equal the energy input. But if you have your velocity in phase with your force, you're pushing in the same direction you're moving, so you do actually end up getting that displacement, because force times displacement equals work, and that's energy, and you use time and you get power. So effectively, if you have force and velocity in phase, you'll have the most power input. That's also the resonant frequency as well. That also provides the phase at the resonant frequency as the most efficient point of frequency of force input. Now that we've talked about the mechanical resonance, let's go ahead and examine an electrical resonance system. So for this system, we have 3 components, not a mass spring damper, but sort of in that order: an inductor, capacitor, and resistor. That's our circuit under test. And we have a forcing function, which is going to be a sinusoidal applied voltage. And you have references to ground. Very different methods of drawing, but ends up having very similar correlations to a mechanical system. For example, in the inductor, the stored energy is equal to 1/2 L, which is the inductance, current squared. You'll find in many analogies from mechanical and electrical systems, you have current being analogous in some cases to mass. We have inductance being related. We have velocity being related to current. We have mass, looking like inductance like I did here. And if you remember in the very beginning example, I compared 1 over the spring constant to capacitance. So that's another thing to mention here. And obviously resistance is losses for a certain current. So that's sort of like our our dash pot, which was related to our displacement velocity. So we have a couple of these analogies here, by which you can understand it's quite a similar system to analyze, and in fact the equation ends up being quite the same. The differential equation would be the inductance, and if we'll do the equations related to charge, we'll call that lowercase q, and q is a function of time, plus the resistance, which is this is current, q differentiated with time is current, plus one over the capacitance times the charge equals voltage. So it is very similar to the mass spring damper, where you would normally have your mass here, your damping coefficient there, and your spring constant in that position. Here, if you remember before, we defined a transfer function in between the output displacement and the input force. We won't be using that because we don't have force, we don't have a displacement. But what we will be determining is impedance. And impedance is defined, as we spoke about earlier, between voltage and current, and also has a phase. So that's going to equal your voltage and your current with a phase. Now this is slightly different than the relationships we derived earlier for the mechanical system, because we typically think as voltage as an input. Now your input's on top. Admittance, which is another electrical parameter, describes current as being an output. But typically the analysis is done with impedance, and it provides exactly the same information. So we'll continue to use that for our analysis. So we'll draw the output of what we'll say is 1 over the impedance. It's slightly easier to draw that, and then we'll convert that to impedance, because this would be your output and your input related. So this would be your output and your input. Then we'll go ahead and analyze the traditional method for representing impedance. So if we have a resonant frequency for a given voltage, we'll have the most output at a resonant frequency, and this would actually be incorrect, because this would be for charge or displacement, whereas at low frequencies you have a finite displacement. Well, at very, very low frequencies you actually have no velocity, because the frequency is so low. Although you do have an amplitude of displacement, because the rate of change of displacement is so low due to low frequency, you actually have practically no velocity, or very small velocity. So velocity would actually be 0 at low frequency and begin to increase. As you get to your resonant point, you still have that resonance response, and you approach a velocity of 0 as your displacement continuously decreases as the frequency does. As the frequency increases, At high frequencies, you are bounded or governed by the inductor. So as you increase frequency, the energy stored or the opposition to flow of current increases. Therefore, you have low current or low, not low velocity, you'd have low current here at high frequencies. And also at low frequency, you have your capacitor dominating your circuit, which starts to behave like an open circuit condition at very, very low frequencies. So inductors and just going over a small amount of the theory here. Low frequencies, and we'll go at high frequency, and we'll go here capacitor and inductor L, and we'll write impedance. So what's the flow of current? A low impedance is a high flow of current. A high impedance is low, so it impedes flow of current. So at low frequency, there is a high impedance, so there's no flow of current. Also, for an inductor at high frequencies, there's no flow of current. However, at low frequencies, an inductor looks just like a straight wire, so it does have a very low impedance. Current very readily flows through that system. However, for a capacitor, as you increase the frequency, the current draw increases. So you have a low impedance. It starts to then look like a short circuit condition. But obviously, as we interact and we put all these components together, we have dominating features, just like mass was dominant at high frequencies for our mass spring damper system. So is inductance here, and the similar case for capacitance and the compliance. So if we go ahead now and actually transfer this to, if we draw impedance now at the resonant frequency, or at very low frequencies, we'll have infinite impedance, and that will continue to decrease as we get to our resonant point. After our resonant point, we will have infinitely large impedance, because we're going back to our inductive behavior. So let's draw that again here, but in this case we'll put both phase and magnitude on a similar plot. So if we have our resonant frequency there, this will be our impedance. And if we look at the phase, now that we have an opposite relationship here, if voltage is ahead of phase, then we have a negative phase there. So if we have voltage here, and if we have current lagging phase, it's negative 90 degrees. And that is different from our mechanical system, where we had velocity or displacement as an output. Now we start from negative 90 and go to 90 degrees. So this is 90 degrees, this is negative 90, and just like we had velocity in phase with force, we have current in phase with voltage here at the resonant frequency. If you do then look at charge, it will be in phase with voltage at low frequency, because it's in phase with the capacitor. It behaves like a capacitor. So this will be at 180. This point right here will be 90. And this point right here will be 0 degrees, the velocity, or the charge. The charge will, this shows the charge is in phase with the capacitor, but however at high frequency we have current, or we have charge at a phase of 180, but the analysis of current shows that we're at 90 degrees. So basically we have inductive behavior at high frequency, capacitive behavior at low frequency, and in between we have contributions from all of these components. And if we in the resistance here, if we have a higher resistance, we're going to have a lower peak magnitude. If we look at impedance, it'll be a lower it will result in a lower minimum. So let's just draw this again. If you have low resistance, you'll have a lower impedance, which would obviously mean more current. And similar the other way, if you have a higher resistance, you'll have more impedance at resonance, which would also mean a lower current resulting output. So you do have to think about impedance as slightly is the inverse of what we traditionally might think of output if you're looking at current as your output, which in most devices we do analyze current as a result of voltage. So we just had a long discussion on the mechanical and electrical resonance systems, and they're actually quite similar. We end up with the same differential equations for their solutions. We end up with similar expressions for transfer functions and impedance, but those again they're inverse depending on the what we're looking at as an output or input parameter. We spoke about a phase change at resonance, and at the resonant point for an electrical system, we have voltage in phase with current. And in the mechanical system, we have our force in phase with velocity, which then gives you the optimal power input, which also happens to give you the optimum amplitude, which is also the natural resonant frequency of the system. So all of those correlate to each other. In the next few slides, in the next part of the video, we're going to describe piezoelectric resonance. And the piezoelectric resonance combines the mechanical and electrical systems because the resonance behavior is largely due to mechanical oscillation, which then drives charge generation. But that charge generation, due to a piezo being a capacitor, then translates that behavior into voltage and current. And essentially, we know that voltage is the way we drive the system. So there are electromechanical relationships that will be described in order to kind of couple these systems together. And we'll also find that the expressions used for force and voltage, they're not completely analogous to each other, but there are, again, those conversion factors which can be used to make effective parameters. After that, we will get into the very important topic of distributed systems, because components don't have a a identifiable spring and an identifiable mass. Rather, the mass and stiffness is distributed throughout the mechanical system that you have attached your piezo to, as well as the piezo itself. So these will be the topics covered in the next coming slides in the next video, as well as the topic of anti-resonance, which anti-resonance is a unique phenomenon where the intrinsic response or the static capacitance response of the piezo starts to couple with the electromechanical mechanical resonance in a very unique way.